Welcome to Train Plastic 411. I hope you enjoy the presentation. My name is Garrett McKenzie and I am the owner-editor of Plastic411.com. Hi all, this is Garrett McKenzie with Plastic 411 Training. The following webinar is Scientific Troubleshooting. It's going to go over using scientific molding and process assessment and adjustment. So this presentation is going to cover scientific troubleshooting. We're going to go over historical data, what data needs recorded and how to use that data for processing, defect scenarios and what critical data best defines changes within a validated process, and also process solutions, how we can effectively make corrections to return to a state of validation. This presentation will be approximately an hour. And you're more than welcome to send questions to training@plastic411.com. So let's first go over processing fundamentals. We're going to go over key parameters in monitoring, analysis, and correction. So in terms of troubleshooting, what are the key factors for troubleshooting a validated process? We have historical data, equipment failures and modifications, changes in tooling, material variations, the labor effect, and also unplanned maintenance. So let's first take a look at historical data. We're going to go over the critical process of data recording. So what is the purpose of recording historical data? Historical data is recorded to define the critical requirements of a molding process. Based on that, historical data serves as a template for a validated process that has been repeatedly proven to produce high efficiencies with little to no scrap. There's no limit to the amount of historical data that we can record. In fact, increasing data collection can only improve a processor's ability to troubleshoot change. In addition, data is collected with the press in good running condition, with the mold and barrel temperatures at a running state condition. We also need to know that the process control limits are established to define requirements for process consistency. Data that falls outside of those control limits trigger a response. Here is a list of recordable historical data parameters. First being fill time. Fill time is a measurement of how much time it takes in the injection phase for the screw to reach cutoff position. Injection speed is a primary driver of fill time. Faster speeds decrease fill time and lower speeds increase fill time. The injection speed also affects injection pressure. Higher speeds equal higher injection pressure, where lower speeds cause a decrease in injection pressure. Historical data can be recorded for each stage of velocity through injection profiling. Fill time for each stage is determined by the change in the injection speed for each position to zero, starting from the end of injection to the first stage. Fill time control limits are generally established at plus or minus 0.25 seconds. Peak pressure is another key measurable in historical data. Peak pressure is the measurement of pressure reached when, at the end of fill, the screw reaches the cutoff position. Cutting off sooner decreases peak pressure, where cutting off in a lower position increases peak pressure. Peak is a primary recordable that should be continually repeated. Control limits should be within 200 psi plus or minus. It should be noted that each stage of injection pressure is also a recordable event. Pressures in each of the profiled injection speeds can help to identify changes within the molding process. Screw recovery time is another key measurable. Screw recovery is a measurement of time as it relates to the beginning of screw rotate to the end of achieving shot size and decompression after rotation. Increasing screw speed lowers screw recovery time, and lowering screw speed increases screw recovery time. In addition, increasing back pressure can increase recovery time, where decreasing back pressure can decrease recovery time. Screw recovery control limits are generally established as plus or minus 2 to 3 seconds in a window. The recording of barrel temperature is also very important. Barrel temperature is another key measurable. Historical data requires both the set point and the actual measurements be recorded. Measurements include both the set point and actual temperatures. And controller data would be a minimum recordable. Measurements of barrel temperature between bands while the press is in a running state increases the amount of historical data available for analysis. Let's talk about melt temperature. Melt temperature is a key measurable that's often overlooked. Melt temperature is recorded with the barrel in a running state, meaning that the press has been consistently cycled for a minimum of 30 minutes. Temperatures higher or lower than the established melt temperature established during the validation verify changes in a molding condition. Melt temperature variations of plus or minus 10 degrees identify process inconsistencies that define process change outside of validated process control limits. Now, an example of this might be that you have a heater band that's not performing properly. The melt temperature was originally 435 degrees Fahrenheit, but now you're getting a reading of 415. That can point towards a problem with the barrel. Now let's take a look at mold temperature. Mold temperature is generally recorded in thermolator and hot oil applications as the set points versus actuals and steel temperature. Thermolator and hot oil temperatures should be equal in terms of actuals and set points respectively. Variations are a sign of mechanical failure requiring service. An example might be that you have a set point of 200 degrees on the thermolator, but the thermolator is running at 170. Well, that could be a sign that the valve's sticking on the thermolator and it's not allowing it to heat properly. Data is collected with the press in good running condition. Mold temperatures should be recorded in a running state condition, the press having run consistent cycles a minimum of 1 hour to assure proper heat soak. Now, process control limits are established to define requirements for process consistency. A normal mold temperature control window would be plus or minus 10 degrees, but it's important to note that process variation can occur in as little as 3 degrees Fahrenheit. Steel temperature is recorded using a thermal indicator at various measurement locations in the mold. Temperature is measured at the sprue, hot runner drops, runner legs, gate areas, and the cavity center. Measurements are recorded on a picture of the mold for future reference. Turbulent flow is another key measurable. Turbulent flow is a measurement of gallons to liters per minute as it pertains to individual water circuits installed to control mold temperature consistency. Now, the measurements are taken at both supply, being the water in, and return, water out. Pressure drop can be used to evaluate changes in the molding condition. Turbulent flow can be increased by using smaller water line diameters on the return side. This increases resistance at supply, which will increase turbulent flow. Higher turbulent flow rates improves mold temperature consistency. Mold temperature is a primary driver of process control, and temperature variance leads to process instability. Part weight is something we also want to monitor. Part weight is a key measurable for identifying process variation. Variations exceeding plus or minus 2 grams on a medium-sized part can be clear indicators of process variation. That window will, of course, increase or decrease depending on part size. Part weight establishes that part consistency has been repeated. Lower weights can cause sink or short conditions. Higher weights can be the cause of flash or other overpack conditions. Part weight variation can be seen as a sign of mechanical change. Worn screw or barrel can be verified using part weight variation. Part weight can also be a clear indicator of changes in viscosity as it relates to back pressure, variations as they relate to regrind usage, or a lot change variation can improve a processor's ability to pinpoint what has changed. The relationship between gate seal and hold time also needs to be verified. Now, gate seal is a key measurable that verifies that hot material at the gate has achieved satisfactory stasis. This assures that material does not flow back into the screw once hold pressure is timed out. Gate seal is measured using part weight. As hold time is added, the part weight increases. Hold time would be set 1 second higher than the time determined that part weight has shown to stabilize. So an example of this would be if the part weight is measured and the weight of 7 grams is repeated, when the hold time is changed from 6 to 7, we would set the hold time at 7 seconds to assure gate seal is consistent. Failure to provide enough time for material waxing can lead to short shots or sink. Too much hold time leads to longer cycles and less profit. Now in this next section, we're going to cover equipment modification and failure. Let's take a look at making modifications to our equipment. Validated processes are based strictly upon what was the current equipment setup and operation. So anytime that we change equipment, such as making an auxiliary change out or do a modification to a machine, we should consider that to be suspect in terms to our validated process. So if we are doing a modification or if we're making a machine replacement, the potential for process modification is possible. We need to review the current validated process and look for variations. If there is a variation or process adjustments have to be made, then we have to consider it a new process, and as it becomes the new process, we must revalidate that process. Auxiliary equipment should be machine specific. So we want to marry our equipment to the press. Anytime that we use multiple units, such as hot runners, thermalators, hot oil units, etc., we can cause variations to our process. Now let's take a look at equipment failure as far as it pertains to variance. As we know, poor performance of machinery can be another contributor to process variation. So our set points and actual data can be keys to analyzing poorly performing equipment. An example might be the barrel temperature inconsistency, which could be a sign of bad heater bands or thermocouple failure. Temperature variance in a thermalator application can identify that valves are stuck open or closed or the heaters are failing. We can also use cushion to identify check ring failure or barrel wear. Failure to maintain consistent cushion will lead to poor process control. Another thing we can do is manual measurement of our dryer supply and return lines. They can identify dryer failure if historical data for normal operation is recorded. A drop in actual supply line temperature can identify a heater failure. A drop in a return line temperature can reveal signs of poor recovery of the heat being pulled from the dryer supply line. In this next section, we're going to discuss the 4 pillars of processing. Heat, pressure, cooling, and time are the foundation blocks of any solid process. Now, in terms of heat, it is one of the primary measurables as it relates to plastics processing. Temperature variability and higher or lower actuals can affect our ability to maintain process consistency. Now, mold temperature can be affected by material temperature, turbulent flow, and water flow rates. And the key drivers of barrel temperature are shear heat and barrel heater bands. Shear heat is actually responsible for 70 to 90% of the total barrel temperature. Shear heat is produced by friction in the barrel as the pellets are converted through the screw from pellet form into a melted state. The heater bands are primarily used to control heat that is ultimately produced by shear heat. Now, by increasing back pressure, we drive more material into the barrel, This increases the amount of shear heat through resistance. Lowering back pressure has the opposite effect, less resistance, which lowers shear heat. The next primary would be pressure. Pressure is another primary control variable. Pressures are measured during injection, at cutoff, and during the hold stage. Now, pressure during the injection stage is controlled by injection speed. Faster speeds cause higher pressures, whereas slower speeds lead to lower injection pressures. Peak pressure is controlled by cutoff. Peak can also be affected by changes in material viscosity. Viscosity change is directly related to temperature change. Higher melt temperature reduces viscosity, causing a decrease in peak pressure, where lower melt temperatures result in higher viscosity, causing an increase in peak pressure at cutoff. Part weight is also affected by pressure. Increases in pressure raise part weight. Decreases in part weight are achieved through lower injection and peak pressures. The next primary would be time. Time is the third primary in the four pillars of a successful processing foundation. There are multiple time parameters that not only serve as set points, they are critical process monitoring considerations. Key time measurements would be cycle, fill, and hold. Now, cycle defines profitability. Failure to meet quoted cycle not only hampers profitability, but can also lead to changes in dimensional requirements. Inconsistent cycles also lead to process variability. Cooling would be the fourth primary in the four pillars of a successful processing foundation. There are multiple cooling conditions that can adversely affect or benefit the overall scope of a validated process. They are critical process monitoring considerations. Key defects that can be caused by cooling time would be long cycle times, warp, dimensional failures, sink, ejection marks, and sticking parts. Cooling also affects profitability. Long cooling times in a process lead to longer cycles and increased job runtime, which affects the overall productivity of a company. In this next section, we're going to go over the troubleshooting dynamics. So what we'll be discussing is key variables for evaluating changes within a validated process. One of the key factors in a validated process would be process control and monitoring. So in this section, we're going to talk about establishing controls and being able to monitor the changes within a validated process. So first, take a look at process control windows. Normal process control windows for factors that affect process monitoring would be as follows. We have fill time, which is plus or minus 0.1 seconds. We have screw recovery time, which is generally plus or minus 2 to 3 seconds. Cushion, which is plus or minus 0.05 inches or 1 millimeter. Peak pressure, plus or minus 100 psi above or below. And melt temperature, plus or minus 10 degrees Fahrenheit, using a probe, not a laser. We also have part weight, which is going to vary depending upon part size. So let's take what we've learned so far and we'll use it to troubleshoot defects. We're going to look at specific scientific molding criteria by the defect type. So let's take a look at how we can troubleshoot flash. So let's take a look at flash. Flash is primarily caused by heat, pressure, or tool damage. If a flash condition exists with little to no hold pressure applied, we're going to inspect the mold for damage. Flash with a feather-like appearance generally points to temperatures being too high. Low clamp force can also lead to flashing conditions. Low pressure can allow the tool to flex, causing flash. Key monitoring variables for flash in a validated process would be changes in cushion, fill time, or peak pressure. The next defect we're going to discuss is splay. Splay is generally caused by moisture, heat, or speed generated by shear. Moisture is generally identified by change and variation. Splay would not stay in the same place or covers a part entirely. If splay is in the same location repeatedly, it generally points to a heat or shear condition. Identify where in the flow front the splay condition is created and make adjustments to fill speed to correct. Keep in mind that burrs in the tool, nozzle tip, or bushing from wear damage can also lead to splay. If splay conditions appear in a validated process, you're going to want to verify that the material has been dried properly and no water is leaking from fittings or the mold internally. You're going to want to review dryer historical data, fill time changes, and barrel set points and actuals. You're also going to want to verify that the melt temperatures are within the established normal condition window. Now let's take a look at troubleshooting sink. Sink can be caused by heat, underpacking, or even overpacking a part. In the case of underpacking, changes to hole pressure are made to fill the part out more. Part weight is a good tool to verify proper pack condition. Overpacking a part can also lead to sink marks. Ribs or bosses that are overpacked resist ejection, causing a pull sink to occur. Adjustments to hole pressure and fill speed can correct this type of condition. Heat sinks often form over ribs or details that hold heat longer than the rest of the part. They are best addressed using barrel mold temperature reductions or increasing cooling time. Now, if sink conditions appear in a validated process, you would want to review your melt temperature, review your mold temperature in a sink area, peak pressure, and look at your cycle time data. Now let's review the next two defects, part warp and stress. Now, in terms of warp, it's generally related to pore shrink conditions. Molecules on one side of the part cool faster than those on the other. This has a tendency to lead to warp. So to correct the condition, you're going to want to cool the mold on the side that the warp is leaning towards. The molecules will move away from the colder condition, thus correcting the problem. Warp can also be caused by a stress condition. In the case of stress, ribs are overpacked, leading to a stress warp condition. Increasing fill speed in the area of the ribs where the stress is causes the flow front to move past the rib detail faster and reduces the overpack condition. If warp stress conditions appear in a validated process, you're going to want to review the melt temperature, mold temperature in a warp area, peak pressure, and fill time data. One set of frequent defects would be burns and trapped gas. Let's address those next. Burns and trapped gas are generally related to poor venting conditions or shear heat created by fill speeds that are too fast. Gas in front of the flow front is unable to escape as the flow front moves through and packs out the cavity. Slower injection speeds in the area of the burn can often correct the condition. If not, then the tool might require new vents or maintenance of current vents. If burns or trapped gas conditions appear in a validated process, first make sure the mold is clean and vents are not splashing out. Also look for changes in fill time or peak pressure. You can also review the melt and mold temperature data for variations to establish historical data recorded. Another consideration might be clamp force. If the clamp is too tight, then it might not be allowing the gas to escape. Something else that could be occurring is if the flow front is going too slow when it approaches a vent, the gas may be able to resist by lack of pressure against the gas, forcing it through the vent. Now let's take a look at flow lines and gate blush. Flow lines are generally related to variations within the flow front as it passes through the cavitation. Nits will appear on the lee side of a detail as the flow front separated to pass around it. Flow lines can be moved by changes to injection speeds and positions. Their appearance can also be improved by increasing pressure. Changes to cutoff position can also improve flow line appearance. Velocity profiling is a key tool for establishing flow line orientation. Each individual stage of injection speed is profiled to identify flow front characteristics by position. Valve gates are another tool for changing material flow. Fill can be controlled by firing gates in sequence using a series of delay timers to establish multiple flow scenarios. If flow lines change in a validated process, review the melt temperature, mold temperature, peak pressure, and fill time data. Also review your hot runner and valve gate setup and set points versus actuals data. Hi, this is Garrett McKenzie, and I hope you enjoyed this presentation. If you're interested in in-plant training at your press, give me a call, 404-793-9834, or you can send me an email, garrett@plastic411.com. Best wishes to you, and make good parts.